So for today's speaker, it's my pleasure to announce this Sasha Mikhailov from University of Leeds. He will be talking on deformations of non-commutative algebras and non-Abelian Hamiltonian systems. So, Sasha, whenever you're ready, you can start.
Yeah, I'm ready for a while.
For a while now.
Right. So I will talk today about our recent paper with Paul van Hakim. And you see my slides, right?
Yeah.
Good. So with Paul, and it is in archive. The paper is big, about 40 pages. And so that is about what are Hamiltonian systems, non-Abelian Hamiltonian systems with variables which not commute. Usually we consider system with commuting variables, how to define and how things works in the non-commutative case. And well, that will be about deformations of non-commutative algebras, Poisson algebras related to that, and non-Abelian Hamiltonian systems. Right. So the plan outline is the following. I will not read line by line. Basically, I will start with motivations. What the motivation examples? Well, in our papers there are many examples, a lot of examples, but I will maybe show only one here in more detail. Simplest one. Then I give some definitions in order to, we have the same language, understand each other, and some tools. And the second part, I will show how the Poisson algebra appears in this, what are Heisenberg and Hamiltonian derivations, and give example of the Poisson structure, etc., on the simplest non-commutative example, and then there is some last speculative slide when I will think what is integrability of such equations. If any question, please ask me at any moment. I will be happy to answer. Right. So let's begin with the motivation examples. Actually, motivation example was a little bit different. I choose the simplest one I can imagine. And we all know about the quantum plane, which is a non-commutative algebra with a commutation relation, so generated by two variables, x and y. And with commutation relation, so if you swap x and y, you have q yx, you get qxy. So, and you can see this quantum plane as a quotient of a free algebra C of q xy. Q is a commutative parameter. Just you can think a complex number if you wish. And over ideal generated, two-sided ideal generated by this polynomial. So basically, every element that are polynomial in x and y, and using these relations, you can uniquely represent every element, putting all x in front and y behind, for instance. That is a basis in this algebra. Right, now let's take an element of this algebra, which is, I will call Hamiltonian in our case, and that is a quantum algebra in a sense, and that element is y minus qx square. If you open the brackets and write it in an ordered way, you will get this polynomial, this polynomial. And then we can commute this Hamiltonian H element with x and commute with y. And then you will see that if you do that, you will have a factor q square minus 1. So if you divide by q square minus 1, you will see something very familiar from quantum mechanics, like commutator of Hamiltonian with x divided by Planck constant. In this case, Planck constant is q square minus 1, or well, IH. I don't care about about Hermitian structure, etc. at the moment. It can be easily reinstated, but we'll make notations a little bit more complicated, and it's not important. It can be done at any stage if we wish so. So don't worry about Hermitian operators, etc. Just look at this equation at the Heisenberg equation, and q square minus 1 is a Planck constant. And that is our quantum equation. And you can easily compute second equation, will be very similar, and that's our quantum equation, basically. Now, what we do a classical limit. And classical limit, when quantum constant goes to 0, and that, for instance, q may go to 1, and if q go to 1, then our algebra becomes commutative, because xy equal yx equal xy, and just algebra of polynomial in xy. And so we go back to commutative world, and we know that Poisson, that commutator divided by nu, which is a Heisenberg derivation, Heisenberg proposed, and that what observation of Dirac, that becomes a Poisson bracket. And in this case, if you do this computation, you will get the log canonical Poisson bracket on your algebra of polynomials. For any A and B, you have a Poisson bracket which satisfy everything, skew symmetric, bilinearity, Jacobi, Leibniz, everything. And then if you do the same with equation has absolutely perfect, excellent limit. You just set q equal to 1. Nothing wrong happen with this part, and you get a polynomial equation in x and y. And your commutator, according to the rule above, becomes a Poisson bracket, and you get a Hamiltonian equation, and h is a Hamiltonian here, y minus x squared just. So nothing surprising. But denominator also goes to 0 if q goes to -1. And if q goes to -1, then the algebra is non-commutative. It's quotient of free algebra over commutation relation yx equal minus xy. So that is our ideal. So the variables x and y anti-commute in this case. And
so isn't it that the squares are 0, or
no, square is not 0, because it's not in the ideal. We have only one relation, yx minus qxy, and q could be equal to 1 and -1, or whatever number you wish. But if q equal 1 or -1, we have 0 in denominator. There is no relation that x square or y square equals 0. If you want, I maybe later I can comment about this, structures related to Grassmann algebra. We have example in our paper when x square and y square equals 0, but that's not in this example. In this example, we just have anti-commutative algebra, so x and y anti-commute, and any polynomial in x and y with complex coefficients will be our algebra here. And if you go with a Hamiltonian, you set q equal -1, you will get x squared plus y squared. Now, if you look on the equation has absolutely perfect and nice looking limit. The only change here is the sign is a little bit different, and just opposite you have some of that. And if you look on this Hamiltonian and you look and you want to take with x, any commutator, anything will not give you this structure, because how you get x square y x square y term, xy, okay, you can think that if you commute something with y square, okay. So the question which arises here, can we write this equation in the form of some Poisson bracket or some bracket with some Hamiltonian h, and give the interpretation of a Hamiltonian equation. That is a simple, that's a question. Let's look another example, which actually was my first motivation, which is not simple. I will not show details, well, unless we have time and you wish, and I can show in the paper how it works. And this example comes from the Volterra chain. In Volterra chain, there are symmetries, infinite hierarchy of symmetries. And if you take the second symmetry here, second symmetry of Volterra chain, it's a cubic in X. So we have infinitely many variables on the lattice Xi. And we have the Volterra equation. I don't write here Volterra equation. I write next symmetry of the Volterra equation. If you look on the next symmetry of the Volterra equation, you will get equation as written here. So as written here, so you have dxl dt equals some polynomial in x and shifts. In commutative case, it's exactly the same equation. But also, you can assume, not assume, you can derive actually using the this quantization ideal approach that I think I give a talk on this seminar and was proposed about end of 2000. That this equation also admits a commutation relations written here, the ideal generated by these commutation relations. That means that the variables xi and xj anti-commute if here should be not equal but more than one. That's correct. I and xj anti-commute if they are not close, if the distance between more than one. And if the distance is one, they either commute to q or anti-commute to q, depending on the index I. So that is a consistent with this system of equation, and you can consider algebra as a quotient over this ideal, and this is a Hamiltonian equation. I mean, not a quantum equation, which has admits the Hamiltonian and can be written in the Heisenberg form, like the equation before. So you commute this h with x, use the commutation relations, and in maybe half a page, you need maybe less, you will derive this equation. Absolutely, no problem to do that. What else I want to say here? Right, there are infinitely many equations of that type there, because there was a hierarchy, and with Sylvain Carpentier and Jean-Pierre Wang, we show that there is infinitely many commuting flows on this algebra. So it's not surprising that we have in commutative case that well known, but on this algebra we also have infinitely many, and we can construct this H to M, M from 1 to infinity, and all this HM will commute with each other, and equation can be written in this form. But look at this ideal. It has no absolutely any commutative limit. Whatever you do, you never go to commutative algebra. In the previous case, we had way q goes to 1, we go to commutative, q minus 1 non-commutative. Here, no way to get to commutative. This variable always are anti-commute, but everything is well defined here, and we can consider q goes to any roots of unity or just one, because one also is non-commutative algebra. In the paper, we consider roots of unity, but here let's look at q goes to 1. The commutation relations here just anti-commute or alternatively commute anti-commute for the nearest neighbors. And the same question: can we write this equation in the form in the Hamilton form or in the limit, because it's not represented by commutator anymore? You can compute, what happens with your Hamiltonian. It's no way to use any commutators. And what are the Poisson brackets between the Hamiltonians? Because before, these are commute as operators. In commutative case, we have standard Poisson brackets, and the Hamiltonians, they also commute with each other, anything, any structure like that. So that was our motivation to try to find the structure behind and discover the properties of this object. Here, I want to draw your attention immediately that these two brackets are different. In one bracket, we have semicolon, and another bracket, we have a comma. And that is the feature of non-commutative equations. And that is why we change one version of the paper by another, because we change the title of the page of the paper in archive, nothing else. The first title was Classical Commutative Poisson Algebra. Then we just Classical Poisson Algebra. Now we have title Classical Commutative, remove classical, because in the classical, these two brackets coincide. In our approach, they will be different. Right. Now let me remind...
The classical is with a comma. The comma is a classical one.
No, it's not a class. In this case, will be not a classical. Neither of them will be classical.
Mm-hmm.
Neither of them will be classical. In classical, these two brackets coincide. And in a non-commutative world, we will have two types of brackets. One responsible for derivation of algebra, and another will responsible for Hamiltonians, basically. They will be different. Now, in the title, there is no in the title Poisson algebra. So Poisson algebra is a Any question? Right. In Poisson, the Poisson algebra is the central object in this theorem, and I want to give a definition. Well, everybody probably knows this definition, but we need to have absolutely exact understanding what it is. So by Poisson algebra, we understand an associative, unitary associative algebra over a commutative ring, which equipped with a bracket. And this bracket is skew-symmetric and are bilinear map of the product of algebra, of two elements of algebra in the algebra. And this bracket is said to be a Poisson bracket if satisfy two identities. One identity is a Jacobi identity, and another identity is a Leibniz identity. So if you have associative algebra with the bracket, we call it satisfying this identity. We call Poisson bracket, and identity and the algebra is called Poisson algebra. And Poisson algebra is called commutative if A is commutative. So if if our algebra A is commutative. If algebra A is not commutative, the Poisson algebra is non-commutative.
Sorry, Sasha.
Yeah.
There are some negative results that never such Poisson algebras does not exist if the algebra is non-commutative.
You will see
only commutators.
You will see this statement or result in a couple of slides, and I will comment on it. Okay?
Okay.
Wait a little bit. Right. And so that is, yeah, the one thing I want to add that sometimes if you don't have Leibniz identity, then a bracket is just a Lie bracket, and that is it is not a Poisson algebra, but we have some Lie structure on the bracket, and sometimes people still call Poisson brackets, and actually Volodya and myself, call it Poisson bracket in our paper when we study equations on free associative algebras. But strictly speaking, in here, we call Poisson brackets, which when satisfy all these conditions. Right. Next, any associative algebra has a natural Poisson bracket. And that's what Volodya just quoted. And this Poisson bracket is a commutator. So if you define this bracket as a commutator of two elements, AB minus BA, then obviously are bilinear, obviously skew symmetric, satisfy Jacobi and Leibniz, and that is a Poisson algebra. So algebra and the commutator is a natural Poisson algebra. There is a story, non-commutative story, history of these algebras. And the first is exactly what Volodya was saying about, that there was a result, 1998, very discouraging result from Vargas Lester, which states that any prime Poisson algebra, which is not commutative, in any such algebra, the Poisson bracket must be the commutator in A, up to some appropriate scalar factors which lives in the center, or well, there are some, basically all commutators, and very little different from the commutator. And here and I will present later example of algebra which is not commutative, but it will be not prime. Because prime, what means prime? Prime algebra means if you have two ideals. Sorry, I have to switch off. If you have two ideals two ideals, well, maybe strictly speaking, Poisson ideals in algebra A, then the product of these ideals, non-zero ideals, must be non-zero. That is a property to be a prime algebra. Of course, most of the algebra we're dealing with are prime, but the example which I will show will not be prime. And that was a discouraging result. And what people thought about that okay, probably we should just change the definition, change the axioms or definition of algebra. And Vandenberg introduced double Poisson brackets, which was not Poisson brackets in the sense which I discussed before, but it's a map from product A to A to tensor product. It was not skew symmetric, but you need to tweak a little bit. You need not Jacobi identity, but also, so does not satisfy the standard definition of Poisson algebra, basically. Then Crowley, Bowie, Bill, and Eckinghoff, Ginsburg, they also kind of dual approach to Vandenberg, and also their algebra was not Poisson algebra at all. Olver and Volodya Sokolov and Olver and Wang also studied Hamiltonian structure of PDEs, but was not on algebra, rather on well, ODEs was of PDEs, of course, was on free algebra, but the Hamiltonians and Poisson brackets was not was defined on the linear spaces, and a similar thing we did with Volodya Sokolov when study ordinary differential equations on free associative algebra. We defined Poisson brackets in quarters here because there is no Leibniz rule. They were defined on a linear space, which is a quotient of our algebra over linear space spanned by all commutators of algebra with itself. And why it is not a Poisson bracket, in strictly speaking, because there is no product in this linear space. There is no compatible product which would satisfy the definition given in the previous slide. Then Victor Katz with his co-authors, De Sol, Valéry, Wakimoto, introduced local, non-local, multivariate Poisson vertex algebras, which actually just translation in the vertex algebra language of kind of results from Vandenberg and the maybe more, well, some people like this vertex algebra language. Was other works like Kontsevich probably was the first who introduced algebras on this linear space, but I have not seen his work published. Then Efimovskaya, Wolf, Chalich, Faron, Kazati, Wang, there are plenty of works in this direction, many works, but they are not Poisson algebras. The closest one is a paper to us, is a paper of Reshetikhin with co-authors, which just appeared on May 28 in arXiv. And I found about this paper when I visit in 1st of April. I give a talk in China. Reshetikhin invited to his, and when I give a talk about these algebras, he said, "Wow, we are doing in a parallel basically the same thing." He has different interpretation, a little bit different results. There is some intersection, but he was the closest to us. But in his paper, there is no Poisson algebra either, although there is some overlapping of the results. Now, we discussed Poisson algebra. Now let's discuss what deformations, because deformations is in the title. By deformation, we understand the following. So let A be any associative algebra over a commutative ring R. And then we consider this algebra as we introduce our formal model of formal series in variable nu. So we have some additional variable, which usually in physics people think like a Planck constant, which goes to 0. That would correspond to a classical limit. And so our nu is a formal power series is nu. So we consider A as our new model over this ring, of the ring of formal series. That means that any element of this model can be uniquely represented as a formal series A naught, nu A1, A2, etc. So infinite series, and every element is element of our associative algebra A. Now we want to, what is a deformation? Deformation, when we equip this model with a structure of associative algebra with some product. So we need to define some product, star capital, big star product. Big star product is must satisfy must be associative. That is the first requirement, and second requirement, the leading term. In the leading term, this product is just product of A and B, like in our algebra. So it can be represented by element AB and AB from our algebra A. So that means deformation of algebras. Now the following notations we use, or maybe open. So if you take a product of two elements, we can represent it again uniquely in terms of our algebra A, and that means it will be a series in nu, and every element here, every coefficient at nu is element of algebra A. So we define the sequence of R bilinear forms, AB1, AB2, etc., that reflect our deformation. And if you take commutator, that will be commutator in our algebra plus nu. There's bracket 1, bracket 2, and bracket 1, bracket 2 are obviously just a difference of these brackets, of these round brackets. So that is about notation. Any question?
Please say again, what is the round bracket?
Round bracket. So you have a product, star product is element of our algebra A nu, right? Of our algebra A nu. And any element of algebra A nu can be uniquely represented as a series, as a formal series in nu with coefficients from our algebra. So these coefficients are our bracket.
Okay, I see. The coefficients are right. Okay, thank you.
Now we go to main tools, which we use, not main tools, yeah, two obvious kind of statements, but I want, because we will use this a lot, you know, that we usually when people working with deformations, they just multiply things, put in Poisson, in Jacobi identity, Leibniz identity, and count every power of nu and prove things in every power of nu that everything works. But there is a more, I think, I would say, not advanced, but more mathematical and economical way to do the same things. But we need two things. One is a Poisson subalgebra. And that is obvious. First of all, we have a Poisson algebra, means algebra and the bracket, Poisson bracket. So what is Poisson subalgebra? Is a subalgebra of A as associative algebra, and also a Lie subalgebra, because we have a Lie structure on our Poisson algebra. And then it is Poisson subalgebra. It must be both a subalgebra and a Lie subalgebra. That is Poisson subalgebra. And similarly, we can define Poisson ideals and quotient Poisson algebra. A Poisson ideal is the following. It's first of all ideal in A, as in associative algebra, and a Lie ideal in our Lie algebra, which associated in Poisson algebra, we have also Lie algebra with bracket. And if ideal both Lie ideal and associative ideal, then it calls Poisson ideal, and it's easy to check. We can give it as an exercise to students that the quotient will also be a Poisson algebra. The quotient algebra over this Poisson ideal also a Poisson algebra. And I will give you one example, and this example is kind of trivial. That is what correspond to the case what people usually do when they compute classical limit from quantum mechanics. In classical limit, in quantum mechanics, our elements are some operators, and the nu is a our quantum constant, our Poisson, our Planck constant. And what is a quantum mechanics? We have our algebra, and the star is a multiplication in quantum algebra in this case, just non-commutative algebra. And we want to find that is process opposite to the deformation quantization. So what we want to do? We want to now use these properties to derive the Poisson structure. And Poisson structure will be the following. First of all, we can see that the commutator of any two elements in A is proportional to our deformation parameter. Indeed, if deformation parameter is 0, then our algebra is commutative. So we start with a commutative algebra A. That is important thing. A is commutative, and we deform it to non-commutative. So commutator is proportional to nu, because if nu is 0, everything must commute. Thus, we can define a new bracket. A new bracket, so when we have commutator, star commutator, we can always divide by nu, and that will be again in our algebra, because nu always there. So we will have, and that means that algebra A nu with commutator nu, this algebra is a Poisson algebra. Now in this Poisson algebra there is ideal nu A nu. Indeed, it is ideal in the algebra A nu, because should start, well, if you multiply any element by that, you will have nu in front, whatever you do. And also it is a Lie ideal, and that is easy to see, because if you commute nu A nu with A using nu, you go to star, and star give you a nu, so we use this property. So that this commutator with this ideal is in the ideal. So that is a Poisson ideal. That is why we can make a quotient. And if you do quotient over this Poisson ideal, that what means this quotient? That means that you forget all the tail which contains nu. You have only the first element in this case. So you can identify this quotient with algebra itself. That is one thing. And if you do quotient on the level of the bracket, you will see that the Poisson bracket in a quotient just exactly coincide with the first bracket, which I defined in the previous slide. And that is a limit, standard limit, what people do in quantum mechanics. They have commutator divided by Planck constant and send Planck constant to 0. So that is, well, you may say that is kind of very extraordinary way to get this simple result, but this way works in non-commutative case. And that's what we will use. Right. Now I want to move to the case non-commutative. Basically, we consider now algebra A, which is not necessarily commutative. It may be commutative, but then we will come back to what I did on the previous page, and I will show you when we get the final result. But it may be any non-commutative algebra. That is the first thing. And let's Z of A is the center of this non-commutative algebra. So that is our notation. Z of A is the center of A. And A nu is a deformation of A in a sense which I described, which I defined before. So we do have a natural Poisson algebra, A nu and the brackets with just commutator from our deformation, because any commutator from deformation is any commutator is a Poisson bracket, as we know. So that is a natural Poisson algebra. Right. Now we cannot do this trick as before in the case when A was a commutative, because if you commute algebra with itself, it's not proportional to nu. So they may not be proportional to nu. It will be just A nu. That's it. And we cannot introduce this new bracket. But what we did, we look on the all examples that we have in hands. That is one thing. Another thing, I will give you another motivation, maybe a couple of slides later. We define a new object where the quantum Hamiltonians actually live. That's what we notice from all the examples, that quantum Hamiltonians lives not in a new, well, in a new, of course, but on a very special place where the first element, which not multiplied by nu, is in the center, and the rest can be everywhere. So let's introduce this H curly nu, which is a center plus nu multiplied by nu a of nu. So the first element in the center, and the rest is in the algebra, and all these elements in the algebra. And then we prove a number of statements. I will, well, everything is carefully proved in the paper. They are elementary statements, some well, they almost all elementary, but, you know, Paul says that we need to put all the proofs, so paper should be self-contained. The first is absolutely obvious, that H nu is a Poisson subalgebra. Indeed, H nu is a subalgebra, because if you multiply two elements from here, you are again here. Moreover, if you commute H nu with H nu, it's easy to see that it is an H nu, because if you commute, the central elements will commute, and you don't have element with in the center, and it's just, you know, you don't have element without nu, and you have just nu a nu, and that is part of H nu. So that is a Poisson algebra. H nu is a Poisson algebra, is a Poisson algebra by its own right. That is one fact. Another fact, less trivial, but also less trivial, but it requires some lemma, is that H nu, we can scale the Poisson bracket to nu. We can divide the star by nu. That means if you commute H nu with H nu, you will see that the result is nu H nu. So you will have nu in front. And that is equivalent to the following statement. If you have any deformation of algebra A, and you take center of this central elements of this algebra and compute the first bracket between these central elements, you will get again in center. You get it back to the center. The proof is quite simple. It requires use the Jacobi identity, but it's quite simple proof. But that is a statement. So H nu with a bracket, H nu with a bracket, scale bracket, is a Poisson algebra. Now let's talk about the two ideals of these Poisson algebras. One ideal is obvious, is nu square A nu. That means if you take a factor quotient of this ideal, that means you forget all terms nu square and higher power terms in nu. So you can consider this ideal, and it is easy to show that it is a Poisson ideal. That is ideal, and also it's a Poisson ideal. And if you consider the quotient over this ideal, you will get Poisson algebra, as I said. And this Poisson algebra is kind of, you forget the old tails. You have element central, you have nu multiplied by algebra, and forget everything behind. So there is a canonical projection of this Z of A and A, so on a pair of elements. And this algebra is non-commutative Poisson algebra, because A is non-commutative. And because A is non-commutative, it will be non-commutative Poisson algebra. And now I answer the question of Volodya, how it can happen. In this algebra is not prime. If you take ideals generated by 0 and element of A, it's a non-zero ideal. If you take two elements of that and you take a product, you will get 0. So that means the product of two ideals will be 0. So there are such algebra, and the Poisson bracket here will be not a commutator. Will be a good Poisson bracket. I will probably comment on the next slide. But what is more important, that nu H nu is a Poisson ideal. That's what we discover. That nu H nu, and proof actually, it's one line. The proof that nu H nu is a Poisson ideal. If you wish, I can reproduce this proof. It's very simple, and it follows actually from that lemma. And because nu H nu is a Poisson ideal of this Poisson algebra, we can take a quotient, and the quotient will be here. Let's look in more detail. So what are elements of H nu? Element of H nu is a sum where first element is in the center and the rest is in the algebra. That are element of H nu. What the canonical projection of H nu by nu H nu? That means you have to multiply these elements by nu, and up to that element you defined. So nothing happens with a node, but A1 will be defined up to a central element. So you can add central element, any central element. And that means exactly that this quotient can be represented as a pair of Z of A and A quotient over Z of A, of center. And so we define object P of A, and P of A is that pair. So the first element is in the center, and second element in the algebra plus any element of the center. It's a coset with respect to this, I mean, with center. And to have more compact notation, cosets we will define with a bar on top. So that has a coset, means the bar. When we write bar, that means up to a central element of the algebra. Now the maybe central proposition, or one of the central propositions we proved. Oh, sorry, the time is going so fast, but I think I have extra few minutes, right? The proposition is that P of A is a commutative Poisson algebra. So that is a Poisson algebra because we proved it before, because that is a quotient of a Poisson ideal. But now I write it in a full detail, because when you have quotient, you need to show what kind of multiplication and bracket come out of quotient when you do the quotient. And here is the proposition that it is a commutative Poisson algebra. Associative is obvious because we have associative algebra and ideal, and quotient of associative algebra over ideal is associative, and our quotient over our brackets will be written here explicitly. So we have two elements of P of A. It's two pairs from center and the coset over center, and the product is defined at here. So the elements of the center multiply with each other, and here we have central elements to element of and plus the first correction of two plus first correction of in our deformation here written, and the coset over center. So that is multiplication rule, and the Poisson bracket between two, which appears as a result of taking all this quotient, will be the first bracket for central elements, and for the second element we will have this longish expression which contains commutator, and first brackets, and even the second bracket, which is absolutely non-trivial fact between central elements. So, and by construction, we don't need to check anything. I mean, the properties Leibniz or Jacobi, because it's guaranteed, because we proved that nu H nu is the Poisson. Now we can go back to the case of when A is commutative, because that is universal construction. What happens if A is commutative? If A is commutative, then center of A coincide with A. Then H nu coincide with A nu. So it's nothing, it's just A nu itself. And P of A is a A nu quotient of nu A nu. So only the first term important, and the rest is zero. I mean, up to the ideal. So we can identify it with A. And if you look here, if you do quotient over center, that every element of a P of A is the first term and zero, because we have second element is quotient over center, and that is zero. So P of A is A, and all what remains from the bracket, only the first bracket remains, and we identify our first brackets with that, and that is exactly the classical limit in commutative case. In non-commutative case, you have more complicated structure. Now, Heisenberg and Hamiltonian derivation. The Heisenberg derivation is defined as we have commutator between H. So we have element H, element A, we take a star bracket, and we divide by nu. That is a Heisenberg derivation. But this derivation is not well defined if H belongs to A. It is well defined only if and only if H belongs to our P of A, nu of A, because if H belongs to A, then the commutator is not proportional to nu, and that object is not living in our algebra A nu. But if H is in H nu, then as we discussed, and then this commutator is proportional to nu can be cancelled, and we have a derivation of the algebra. That is a Heisenberg derivation. That means again that our Hamiltonians must live in H nu. Now we can take a limit here. Nu goes to 0 from this commutator, and what we get, usually we get some bracket. Now, what if you do this? The first H naught from the center and A will give you the first bracket from the deformation theory, that from our deformation, and we also have H1 with A because it's proportional to nu and divide by nu, and H1 is non-commutative part, and A may not be non-commutative, they non-commute. So our bracket will be, our derivation will be extended by one extra term. It's like when you have a non-commutative theory, derivations always kind of extended by some commutator. That exactly the extension that appears, and that was independently discovered by Reshetikhin and his group, and they call it hybrid derivations, and they promote the idea of hybrid systems like classical and quantum systems. In our case, we say that is exactly Hamiltonian derivation, because that is in a commutative case, that how it appears, and that is a bracket. So we define a Hamiltonian derivation of algebra into itself, with any element of P of A, of our Poisson algebra P of A, with any element of this Poisson algebra, we define the derivation of our non-commutative algebra, and we prove that it is derivation. So that means if you have products, you know, you just the Leibniz, everything Leibniz, linearity is obvious, and Leibniz need to be proven, but it is proved. You know, it's easy.
Sasha, what about the commutator of two Hamiltonian derivations?
I will show you in the next slide.
Okay.
Right. Now, actually, we discover the model structure of Poisson, Poisson model structure of associated with this construction. So we have our Poisson algebra, the P of A, with a bracket defined on the previous slide. I can show you this bracket again, this bracket. And there is a Poisson algebra, Poisson model structure, and Poisson model has two. It's a bimodal. It has two operations. One is multiplication, and here is a multiplication in this Poisson model, and a Lie structure, and that is a Lie action on the Poisson model, exactly coinciding with this derivation. Look, Lie structure. Well, that is a definition of a Poisson model, but I will probably skip it at the moment because I don't have much time. If you wish, I can come back later when the seminar finishes. And that is answer to Volodya's question. So if we have Poisson, so we have, we call that Hamiltonians, elements of P of A, we will call Hamiltonians, you know, can call Hamiltonians. It's not elements of algebra. It's element of P of A. It's a pairs that we call Hamiltonians. And Hamiltonian equation is defined as a bracket, these brackets with semicolon. And bracket with semicolon is the following. So we take element of algebra and element of P of A, and we build this thing. That is the derivation, and that is Hamiltonian derivation. That we call non-Abelian Hamiltonian equation. So A is non-Abelian, element of algebra, H not element of center, H1 is element of the coset. Actually, see that that should be element of the coset, because if you add center to H1, it will disappear in this commutator. The center will just die out here. Center never affect this equation. So that's correctly defined on this equation. Now the answer to Volodya's question, that if we have two Hamiltonians, we have two derivations, and if you commute the derivations, that will be derivation of a Poisson bracket of elements f and g, and that Poisson brackets is in the algebra P of A, that the longish one, this one. So it's exactly, and what we have, and of course we say that Hamiltonian are in involution if this longish Poisson bracket is zero. And then these derivations commute, so we can define commutative flows, etc. I draw your attention that in this case, the difference and why we change the title of the paper, why we have a second version in archive, because first, you know, we were excited and called like classical, but then I say, come on, call, it's not classical. In classical, these derivations coincide, and we have the Hamiltonians live in the same place as our algebra. And here we have two different. We have algebra itself, and we have derivation of algebra defined here above. And we have also derivation on PA, which is defined by the Poisson bracket, you know, in our Poisson algebra. So we have two derivations, and they are very, of course, much related, but none of them define another. So if you know one derivation, you cannot define the second one. You know, that is well, not directly at least. And in the commutative case, A coincide with P of A, and these two derivations coincide, and these brackets coincide. So that is a classical case. They coincide. In our case, they not, because here we have some extra term, and also you have two sort of objects, one non-commutative algebra, another commutative Poisson algebra. Did I answer your question, Volodya?
Yeah.
Good. Now, why commutative Poisson algebra so important? I thought, and I asked this question many people, and now I start to understand it. It is important because it is sufficient to find the Poisson brackets only between the generators of this algebra. And if you find generators, then the things like partial derivatives are very well defined. It's not like in free algebra, we have a partial derivative, it maps algebra to tensor product or algebra of left and right multiplication. No, it will just a partial derivative, that's it. And we can use a standard Poisson bracket. We just need to find all Poisson bracket between the generators of our algebra, of our P of A. And that is a commutative algebra, as I, stated. As about Hamiltonian derivations, because it's a derivation of algebra, it is sufficient to find the bracket, this bracket with a semicolon between generators of our Poisson algebra and generators of algebra A. So that is a very finite, small, well, finite, if system is finite dimensional, it's a small table. And then you can find every Poisson bracket between anything you want, just applying a standard formula, standard rules, like before. Now I want to, it's almost finished. I'm sorry, I'm a little bit longer, but I start a little bit later. Let's go back to example quantum plane with Q equals -1. So that is it. Deformation of Q is near -1. So Q goes to -1 when nu goes to 0. And that is our quantum plane. What we can say immediately, that quantum plane, if Q is not a root of unity, then center is just coincide with the complex numbers. The center basically pulls, basically just the field, the field of constants. There is no any other elements in the center. Center is very, very small, and you cannot do anything with this center. But if Q goes to root of unity, then center will be generated by x power n and y power n. That is the fact. So what goes when nu goes to 0? That our algebra, this algebra, we can identify with our deformation A of nu. So we just any elements when we commute, you have a polynomial in nu. Well, polynomial formal series does not matter. Polynomials also formal series, but a little bit short, belong to formal series. But our algebra will be a quotient over this anti-commutator rule. Now, how we, so that is our star. Any star, how we handle star and how we represent it in terms of our algebra A. Very easy, we just take this star and if you multiply x by y, it's the same x by y, because we use basis x power n, y power m. and the constant, you know, that is a basis of our algebra, and every element of our algebra, of this algebra A, can be uniquely represented in this basis. So what we do, any product, we just write in this way. So if you multiply y by x, you have that. And if you multiply any two elements, you just take a normal ordering, means put all x's in front and y's behind. And then you have all your brackets, small brackets, you know, which I defined here, like you multiply two elements. Nothing will happen if you multiply these two elements. But if you multiply that two, you need 6 times to move letters, and then you have this polynomial. You can expand it, and you get the first bracket will be just x. Well, you see, this algebra is not anti-commutative. All elements, center of this algebra generated by x square y square. The quotient of this the quotient of this algebra A over ZA can be seen as ZA module generated by 3 elements, x bar, y bar, and xy bar. So x plus, and the ZA model shows that any element from here is any polynomial of in x square, y square multiplied by x bar, by y bar, and xy bar. And 1 belongs to center, of course. So the algebra is generated by 5 elements. That is 5 elements. And according to our multiplication rule that I shown, may show again, this algebra is commutative. This algebra is commutative and is actually equal or whatever to the quotient algebra, to the algebra of polynomial in these letters x, y, u, v, w, quotient of the ideal generated by these things, and this things tells you that product of u, v, w in any order is just 0, basically. So that we have commutative algebra. What we need now in this commutative, and Hamiltonians live here in this algebra. And we need to compute Poisson brackets between Hamiltonians, or in this Poisson algebra commutative, we need to find all Poisson brackets between the generators. And that is a table of Poisson, all Poisson brackets between the generators. It will be easily computed. And that is in detail shown in the paper. To compute the Hamiltonian equations, we need two Hamiltonian derivations. The operation in this PA Poisson model A. So A is the PA Poisson model. That means we have products in this model. It is here, and we have a semicolon bracket between elements of our PA Poisson algebra and the generators of algebra A, and that is a table of that things. So if you take now Hamiltonian and you look from this Hamiltonian, you need to consider the corresponding element of the quotient as I described before. Basically, you need to consider element at without nu and proportional to nu. Without nu must be in the center, and that is h naught. And with nu, it will be the h1. So if you look here, you will see that you have y squared divided by 2 minus x squared divided by 2 minus, and that is x and y, our capital, and xy bar, that will be w. Now, if you compute our Poisson bracket using this rule, using the rule above, and you will get exactly the equation that we wanted. So that is a Poisson derivation. The Hamiltonian derivation give us this equation. But that basically, maybe I can answer the question to Satiris. He said that x square 0. Indeed, there are such situations. For example, if we consider boson and fermions in quantum case, then fermion variables anti-commute to a Planck constant, and boson variables commute to IH. So, and that can be considered as a deformation of a Grassmann algebra. And Grassmann algebra is non-commutative algebra because we have commuting, non-commuting elements. If you just apply this construction to that case, and that is done in the paper as a kind of simple illustration, you can find all these tables and you can reproduce Poisson structure, and this Poisson structure will be exactly coincide with known graded Poisson algebra, which people use in the super mathematics. Not exactly coincide. It will coincide because we don't ever compute Poisson brackets between generators of the algebra. We compute Poisson brackets between generators of this P of A, and also semicolon brackets between variables in P of A and here. And that it means we reproduce only part of the brackets which people use in the super mathematics. But this part is sufficient completely for the for writing all equations and the Hamiltonians and everything what we need. We never use Poisson bracket between variables, between odd variables in this case. So we don't need brackets with a plus, and we don't need to modify the Jacobi identity. If you have Jacobi identity, it stays forever. You know Jacobi identity. So that's what happens if you, and then you can put, you know, the square of variables is 0. That is everything compatible, everything works. And the last slide is here. That well, more or less trivial, but I mean, Paul not agree with me, but does not matter. It's my talk today, and he does not attend. So that what is happens is in classical mechanics, we have kind of everybody agree that there is a Liouville integrability. So is in Rn we have n functionally independent first integrals, and we have Poisson's bracket. And if these integrals are in involution, so the brackets are 0, and we have a complementary number of Casimir elements of the Poisson bracket, then we call the system Liouville integrable. And if you have a quantum reincarnation of this system, and we have n commuting algebraically independent elements of our quantum algebra Hn, which are Hamiltonians or whatever, which because they commute, they can be simultaneously diagonalized, and also complementary number of central elements of this algebra, then we get people consider this as integrable. Of course, that's a big difference, because in the first term we know how to find the change of variables to reduce problem to quadratures. In the second case, we only have the theorem that they can be simultaneously diagonalized, but it's a far from the solution of the problem. But still, people like to call it integrable. And here, obviously, the central elements of quantum algebra in our limit will give us Casimir elements of our Poisson structures that we derived in non-commutative case. And you can say, okay, if you have n, we have now Poisson brackets well defined. If you have n algebraically independent elements of our Poisson algebra, which are in involution, and the complementary number of Casimirs of these Poisson brackets, and these Casimirs also Lie annihilators of our algebra, that is easy to show, then we would call this system integrable. But how to solve this system, we not yet know. And maybe the paper of Reshetikhin is close, because he tried to address this question. Although I'm not completely completely agree with his philosophy, because his philosophy is that that he says that it's like Oppenheimer Oppenheimer approach, that we have some classical field, for instance, and we have a quantum atom on some classical field, and we need to have kind of classical description is natural for classical pattern motion and quantum for atom. I don't agree with that, because in our limit, although he consider kind of same limit, in our limit, the quantum constant nu completely disappear. So it's not a quantum system anymore. It's a system on a non-commutative algebra. And what I think what we did is exactly the formulation of non-Abelian Hamiltonian systems and the associated Poisson algebra and Poisson model. So that's basically all what I want to tell you today.
Okay, Sasha, thank you very much for a very interesting talk. Any questions or comments?
Sasha, hi. Maybe, I don't know, any applications of this, like theory?
Well, you know, we have quite a lot of now people. Suppose you have a quantum system, and we in quantum system you have your quantum parameter, and this quantum constant, and if this quantum constant, which is in your Heisenberg derivation, and then you want to consider the limit when this constant goes to 0, and if this limit is classical, if algebra is commutative, then you reproduce a standard Hamiltonian equations. But if it is not commutative, what we claim, we get a system which has the same kind of structure and the same almost the same picture. The only difference that we have Hamiltonians live in one place, and we have we have algebra, and Hamiltonian lives not in this algebra on PA, and we have two different brackets. So we get a structure which reproduced from this system. What Reshetikhin study also a similar thing and related to I think to Rasenar system and to some configuration, and so if you get, you know, if you get this limit, then the system already not quantum from one side and not classical yet, and so that is a way how to approach to this system. I don't know how to solve this system, but there are several questions. Can we, for instance, we have a deformation quantization. So we have a Poisson bracket, and then we want to deform algebra such that the first correction will reproduce this Poisson bracket and make an associative non-commutative algebra. So go to quantum case. Here also there is interesting question. Can we do that? Can we do these things? And one more fact I want to tell you, that we prove the following statement. If you have deformations of algebra, just algebra deformations, you have algebra, and you have in this case non-commutative algebra, and we have non-commutative algebra deformations. Actually, this is not very well studied thing. And then deformation may be equivalent. Equivalent, that means you have some homomorphism also as a in a series in your deformation parameter, which may map one algebra to another, right? So what we proved that if deformations are equivalent, then the Poisson algebras are equivalent. And what we have found, that we have found 3 different Poisson algebras on the same non-commutative algebra. One comes from 2 comes from Volterra chain of period 4, and one from quantum groups, or more exactly from you know, this matrix algebra M2Q, which is an endomorphism of quantum plane, which maps elements of quantum plane to itself. So this algebra, if you look at this algebra at q equal roots of unity minus one, minus one, for instance, then they are not equivalent to the other. We have the same algebra A, but three different deformations we have, which are not equivalent to each other. That is another thing. And if this, yeah, but the immediate applications, I don't know.
Yeah, I see. Thank you. So yeah.
Sorry, Sasha, is it possible to formulate all these things in the language of Hochschild cohomologies? This is about deformation of associative algebras.
It's about deformations of associative algebras, yes, indeed. But you know what you ask me? No, we did not do the problem. We did not study the problem of deformations themselves. So we just yes, the deformation is related to non-trivial cohomologies, right? But we did not study that the problem itself. So we just take any deformation which exists, any deformation which any deformation of a non-commutative algebra, and with this deformation we can associate this structure. Of course, there are some deformations. There are trivial deformations or very simple deformations, like you can just multiply your ring of formal series to the algebra, right? And that will be also kind of trivial deformation of the algebra. And you can do this. You will get very simple, very simple Poisson structure, which is nothing interesting in this Poisson structure. It depends, of course, on the deformation. The deformation should be of the following. The deformation should be very special. Namely, when algebra is undeformed, then we have a big center. And when you deform, the center kind of change. Because if center is the same, the center of deformed algebra, gives you only Casimir elements in our structure. So, and the center should change. In all these cases, oh, well, I may probably show you why it is important. Let me go somewhere here. Somewhere here. Look, what we do no, let's go to the first slide. Like that. Look, if you look at this equation, you can multiply. So what limits we look? We look at limits when denominator goes to 0, right? That is correspond to Planck constant goes to 0. Now let's multiply by denominator the whole thing, and then what you will get, that the commutator of H with every element of generator of our algebra. And if Q goes to if Q goes to 1 or minus 1, you know, you will get 0. So that means your H will go to the center of the algebra. Like in this case, when Q goes to minus 1, our Hamiltonian, goes to x squared plus y squared, and x squared and y squared are generators of the center. So it goes to the center. It was not center, but goes to the center. So we need consider not just arbitrary arbitrary deformation at arbitrary point, but we need deformation of algebra such that it will destroy the center. So we have algebra with a non-commutative algebra with the center, and we have a deformation which kind of destroys the center of the algebra. And if deformation removed, we get a big center or subcenter of the algebra.
Because so these non-trivial deformations can be defined in terms of Hochschild cohomologies or not. Some cohomologies are trivial or non-trivial.
No, of course it should be defined can be defined in this term. I discussed it with Paul, and well, we did not go this way yet, and because I think there are better equipped people to do this job. Yes, it's related to second homologies. Yeah,
It should be.
yeah. But you know, important thing what we start with, because you cannot start from any algebra, right? No, for instance, I ask you the question, what about deformation of free algebra? It's non-commutative, right? Can you deform it? Because now people try to find Poisson brackets, Poisson structure on free algebras, and I saw a few attempts to do it, but I didn't see any successful.
I can also ask two questions. So one question is probably what you were explaining, probably I didn't catch it. So you have the definition of complete integrability for your quantization version of the systems. Do I understand correctly that no, that the systems with which are completely integrable, the quantized ones, do not have the property of the Liouville theorem that they can be integrated by quadratures in terms of integrals?
No, I don't think so.
Mm-hmm.
Quantum,
But maybe could be actually, but because for matrix systems, I think is the same. But the thing is, well, I know that your job is not modeling, but the question is, well, the second question is the following. So, well, the non-commutative versions of systems, like in Volodya's Sokolov book, which are matrix versions, that is you see straight away that they can model real physical problems. Do you think that real physical problems can be modeled in this kind of quantization?
Well, that is an interesting question, and I can speculate on that in the following way: that you know there are when physicists try to build a model like nucleons, etc., they use intuition based on what they know, and what they know that there are commuting, anti-commuting things. But then were attempts to introduce parafermions, for instance, which are not Z2 but Zn graded, right? And that means your algebra will be in the limit is not Grassmann algebra, but you have a different grading. And here is a kind of well, there are two things. One is quantisations and find different well, basically the work that I was thinking about, the problem I was thinking about, that how to define correctly equations on differential equations or models on algebras. And that is not really, and that is very close to quantization. And that's what, and everything should be consistent. Well, when it's commutative, no question. But when it is non-commutative, then there are when it's non-commutative, then the equations should kind of obey these rules. Should be consistent with algebra. Even in the first paper of on quantum mechanics by Dirac in 1925, he raised this question. He says that, well, these Heisenberg commutation relations should be compatible with all dynamics and everything for finite value of a Planck constant. We know that if constant goes to zero, well, he showed in his paper, the commutators, everything goes to classical mechanics, and here we say that we know that everything is compatible, but for finite of these constants that need to be proven that it is compatible, and that is a kind of non-trivial question. And one of the problems that what I am interested in to find what algebras are and what kind of algebras and what kind of equations we can write which are compatible with algebra and with everything. And that was the idea to introduce these ideals of quantization. So in
Sorry, Sasha,
yeah.
but why you cannot say that equation is a derivation of algebra and integrability means that you have a lot of derivation which commute with this?
Equation is derivation of the algebra. Look, not well, yes, that is a question about the derivation of the algebra, which is a not trivial question. If you look, of course, you always have in the derivation of algebra, but no, I think it's no, for instance, you remember when we did, with on classify equations on free algebra, we know how to do it. But then to do the same on some, if you impose algebra, then it's difficult to approach to this problem.
I understand, yeah. It's difficult to define the derivation, to describe the derivations because we have some relations.
Yes,
Yes.
that relations. And that is why I introduced this quantization ideals, because if you have an ideal which, is stable with respect to derivation, then the quotient will be automatically everything consistent. The equation will be well defined on this algebra. The problem is how to represent things in the. Can we always represent it in the Heisenberg form? And no, I'm talking about physics. I want to say that probably there are other things which people did not look, and the intuition is based on what we know. We know commutative, anti-commutative things, but maybe there are some others.
Well, you should definitely give a talk to a physics conference.
Yeah, but maybe there are some others, and well, in physics, I can say we just sent a paper with Taras about simple question about the Euler top, or maybe Euler top also in external field, and that is commutative limit, of course, in this case. But even in this commutative limit, you can find 4 compatible Poisson structures. And in quantum case, basically we first find quantum, and then the classical limit give us these compatible Poisson structures. Easy to prove then. But even in quantum case, you have 4 five-dimensional 5 quantum constants. One is Planck constants and 4 other constants. And physicists use only one. And if you ask why, because they say that, oh, in mechanics it was that one. But why in mechanics was that one? Why sometimes we don't know how objects is organized, like a nuclei or nucleons, and how these quarks or whatever. Because that is our model. That's how we try to present things, and we present from this puzzle from the things we know, which we have in our hands. And the question is it sufficient? Maybe we need to make a richer collection of these forms, shapes that using in our modeling of the world. If we cannot do it, with existing things.
Yeah, okay. The topic is very interesting. I don't think we can discuss all several questions. I think we should postpone for another time. But it's very interesting. Thank you very much.
Questions.
Sorry?
Thank you.
Any mathematical questions?
Yeah.
All right. Okay. Thank you.
Okay, thank you very much. And see you. Bye.